Good afternoon. My name is Rudrapatna Shyamasundar from the Indian Institute of Technology, Bombay, and we have a validator node that is supported by under the UBRI scheme. So today I'm going to speak a little bit about, it's a short one, towards a robust AMM on XRPL using threshold encryption. I think you must have seen already many trading things in this context of high frequency trading and also decentralized finance. Robustness becomes an important issue for everything or the other. People may question, people have to be aware, a normal trader have to be aware that there are no attacks so that he can really be doing what the algorithm he is doing it kind of a thing. So just to brief, one of the popular mechanisms in prediction markets other than the continuous double auction is the automated market maker. It allows traders to place all orders with the AMM and determine the cost of each transaction and adjust the prices of the securities. It has several advantages for a prediction market trading at all hours, as somebody mentioned in many of the talks, reacting instantly to changes in trading and eliminating unfortunate spreads that are found in thinly traded markets. For AM to be useful, there are a couple of conditions that needs to be satisfied. The underlying algorithm should not be vulnerable to becoming a money pump to a clever trader. So that is one of the things. And its potential losses should also be bounded ahead of time, having tunable properties. So now, just to take a look at how the consensus algorithm in the XRPL works. So here you have, everyone knows, but I'm just repeating, every non-faulty node makes a decision in a finite time. All non-faulty nodes reach the same decision value. 0 and 1 are both possible values for all non-faulty nodes. This essentially means the trivial solution in which all nodes either decide either only 0 or 1 regardless of the information they have been presented. And these are all some things or the other. So now if you take a very broad look on the XRPL protocol consensus, this is a rough view, a broad view rather than a strict view. Each server takes all valid transactions seen prior to the consensus round that have not been already been applied and makes them public in the form of candidate set. May include new transactions initiated by end users of the server transactions held from the previous consensus process, and this becomes important when you are looking at the next, when we look at the privacy. Each server then amalgamates the candidate sets of all servers on its UNL and votes on the veracity of all the transactions. Transactions that receive more than a minimum percentage of yes votes are passed on to the next round. Transactions that do not receive enough votes will either be discarded or included in the candidate set for the beginning in the consensus process on the next ledger. Final round of consensus requires a minimum percentage of 80% of a server's UNL agreeing on a transactions, and all transactions that meet this requirement are applied to the ledger, closing it, and that becomes its last closed ledger. So in summary, if you look at it, every UNL needs 80% nodes to agree at a single point of decision, as the network cannot tolerate more than 20% faulty nodes. If you look at the general block transaction flow, user broadcasts their transactions. The transaction goes to the mempool and miners orders them. So now here if you look at how do we do XRPL, use it for the AMM, what is the challenge? That is, the minor extractable value or the maximum extractable value is the value that a participant can extract within the system by strategically placing their transactions in front, middle, or later. As you will see, users create unintentional MEV in trade transactions, spillage to accommodate the market price. Privileged participants within the network can make profits extractable on a first come basis. How do we overcome or minimize such things or the other? For example, if you look, this is the structure what I mentioned. All transactions come to the mempool and the miner orders them, and then you get the block of transactions that are ordered. So now here, the transaction order dependence is the state of blockchain updates with each transaction. Token transfer versus token trade, buy and sell. For example, here you have the token praise. A user makes an order, let us say for 1,000 tokens. An adversary observes this order and makes his own order, and then he gets it, and now later that becomes much more kind of a thing or the other. So now here you can classify into different attacks. One is the front attack, front running attack, that is the one which comes in the front. I come first and then you become later, and back running, this almost leads to a denial of service kind of an attack. And sandwich, of course, as you can see, it can come in between or the other. So now here, what it means is that because it is public, everyone can observe what is the transaction he has put. So the only way we can try to overcome the reordering of the transaction is to make it private, so it becomes encryption. So like there have been many threshold public encryption algorithms started from Bonnet et al. And then here it has a single public key and distributes the private key among n description servers such that at least a threshold number, say k, are needed for description. The use first a committee corresponding to the decryption servers is set up such that its members have the distributed private key. All users encrypt to the committee's public key. Miners can only see encrypted transactions in the mempool and create blocks containing ciphertext. With the confirmation of the block, the committee jointly decrypts all transactions that are included in the block and announces them to all the nodes in the network. So now what are the issues in the existing things? Malleability. An adversary could create a related transaction ciphertext, submit that instead, and learn information about a transaction which has not been included on the chain. Another one is the pending transaction privacy. A new encryption scheme, clients encrypt you an epoch, and then the decryption key is the same for all ciphertexts, and this leads to unacceptable compromise to privacy, as ciphertexts that are not done on the main block, they become available, and this is treated as the pending transaction privacy. So now this one was solved by Arkarai Choudhury et al. In the Usenix 24 paper. Unlike the naive use of the threshold encryption, which requires communication proportional to order of NB to decrypt B transactions with a committee of N parties, the batched threshold transaction requires only order and communication. That means it is independent of the block size. Communications required to decrypt an entire batch of B transactions is only 80 bytes per party, independent of the number of transactions in the block, making it an attractive choice when communication is very expensive. So now here, the question what you have to ask is that use batched threshold encryption on XRPL works without forks. If there are no forks, then the whole batch thing works or the other. But now, however, with forks, because if there is a possibility of a fork, then that has to be decrypted, and then that becomes available to the public, and it becomes a problem or the other. So now here, in the context of what we have seen in the XRPL, in the earlier paper, what we showed, because there have been many things to say, how many of the nodes have to be satisfying certain conditions across the UNL intersection kind of a thing. In an earlier paper last year, we showed that using some notion of a similarity, which is used for clustering, we showed that exactly in the current context, using this similarity, we can show there are no forks on the other. So that essentially means now the batch, the BTE works without any problem, and so we can preserve the privacy. That essentially means that it becomes robust because no front-running attack or the other attacks can happen or the other. And so now here there is always the arbitrage problem or the other. This is a well-known concept in XRPL components or the other, because you have various transaction types like a payment offer create, offer cancel, trust net, and there are many flags, and XRPL does not allow a cross currency. That means a payment cycle from XRP to XRP itself. So now here, this one you can show that using Bellman-Ford algorithm for detecting cycles, you can find out if there is a negative cycle, you can see that there is an arbitrage kind of a thing. To summarize, I'm not going to detail because of the time. AMM on XRPL using batch threshold encryption realizes Mempool privacy. And now the question is that arbitrage, whether under regulations it is good on some cases and it is bad on some cases, and that is something that one has to do. How much MBB, the fundamental question would be how much MBB can be overcome or minimized. It depends upon issues of synchronization, some of these which I have touched upon on the issues of ERC10, ERC20 problem or the other in the Ethereum because of the high level of synchronization that uses. Thank you for listening.